Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. BS Physics, Semester 1, Mechanics 1, Course Code Physics 1103, Lecture number 14, Chapter number 4, Circular Motion. The lecture is named as Relativity, Relative Motion, Relative Velocity, Relative Acceleration, and the Galilean Transformations. Dear students, I am talking to you, Rashmat Ali, Assistant Professor of Physics, Khaja Fareed Government Postgraduate College, Remia Khan. Dear students, the material of this lecture has been taken from the outlines of BS class and the book as recommended by the University Physics for Scientists and Engineers, written by Survey Javed, and another book, Fundamentals of Physics by Gerald Walker. First of all, the main contents: frame of reference, relative motion, Galilean transformation, and finally, acceleration is independent of relative motion. So, relative velocity and relative acceleration. First of all, the frame of reference. Reference, we take some body's reference, and the frame of reference is a set of coordinate axes relative to which measurements are taken is called frame of reference. It has two types: inertial frame of reference and non-inertial frame of reference. Frame of reference is quoted only for the reference. As details we will study in later chapters. Relative motion. We know the motion. If a body changes its position continuously with respect to its surrounding, it is known as motion. And relative motion, this motion is described by one body or more bodies and some other bodies. Motion of body with respect to another body is called relative motion. The observations made by different observers in different frames of references are related to each other. Observers in different frames of references may measure different positions, velocities, and accelerations for a given body. It means that if a position, velocity, or acceleration according to single observer has certain values, it may be the same values or different values for other observations. We explain, understand that this quoting consider two observers moving relative to each other generally do not agree on the outcomes of measurement. Maybe both have the different measurements, different outcomes, different results. Now, if two observers are watching a man moving on the beltway, see in the figure, this is the beltway, a man is moving on the beltway, we can see easily, and two observers, one a gentle lady standing still on the beltway, where the beltway is moving, and in another gentle lady is observing at some distance away from the beltway. We can see the man is moving and beltway is also moving. According to the lady standing on the beltway, observes that the man is moving with normal speed. And according to the lady standing away from the beltway, sees that the man is moving with more speed, and the lady is also moving with the belt. So, two observers had different ideas about the same moving body or stationary body. Similarly, if a moving body takes the notice of stationary, a gentle lady standing on the beltway, if she takes the notice of lady standing near the beltway, she finds himself as a stationary, but finds that the lady is moving backward. Relative motion. Suppose another example. A man is moving on a scat, also throwing a ball in his hands vertically upward. We can see here, he sees himself, the ball moves up vertical and then goes down vertically. But to a man B, who is observing stationary to the activity of a man moving on the scat A, he observed that the same ball as follows the path of projectile shown in the red curved line, parabolic line. Suppose a person is riding on a scat, board A throws a ball in such a way that it appears to, in person's frame of reference, to move upward first, then straight downward along the same vertical line. An observer B on the road sees the path of ball is parabola relative to B, ball as a vertical and horizontal components of velocity, projectile motion. Similarly, another example, an airplane is flying, a package is dropped from the moving flying airplane with uniform velocity. Observer in airplane sees the package is falling vertically downward below the plane towards the earth, but to an observer on the ground, the package follows the parabolic path. Transformation, the change of coordinates from one frame of reference to another frame of reference, is known as the transformation. Galileo is the first who related the coordinates of both frames, among which one of them is at rest and other is moving relative to the first one. So we define the Galilean transformation as the set of equations that help to transform the coordinates of one frame of to another frame of reference in relative motion, first studied by Galileo, are called the Galilean transformation. Consider a particle is located at point A. See this figure. Relative to two frames of references S and S prime, at t is equal to 0, when time is going to start, both frames overlap, that is S is equal to S prime. Both have the same coordinates, no change in the coordinates. Let the S frame is fixed on the earth and S prime frame is moving with velocity V naught towards the right relative to the frame S. The distance moved by the S prime frame is V naught t, as shown in the figure O to O prime. The second frame S prime is moving with velocity V naught towards right. At this instant, at time instant t, both have the different coordinates. From S prime, the position vector is R, and from S prime frame, the position vector is R prime. This triangle shows all three vectors are joined by a head to tail rule, so that V naught t is the distance displacement in the V naught direction of velocity R prime, both added to get the R. So the motion of frames, here we saw that S prime is moving. In other words, if somebody is observing in S prime frame, he can conclude that S frame is moving towards left, but its velocity will be minus V naught. At time t, the origins of the frames are separated by distance V naught t. R and R prime are the position vectors of the point A from S and S prime as in figure. From figure we can see that R is equal to R prime plus V naught T. In other words, R prime is equal to R minus V naught T. This set of equation transform the positions coordinates xy coordinates are R and R prime coordinates. Now differentiating the last equation R prime R minus V naught, we get the value dr prime over dt is equal to dr over dt minus V naught, where V naught is the velocity of S prime and dr over dt is the velocity of the frame, relative frame change in position from S frame. These are the transformation in velocities, the coordinates of velocities. These two set of equations are called the Galilean transformations. When two frames are moving relative to each other, their positions are changed, can be transformed, and velocities can also be transformed. What about the acceleration? There is a conclusion about the acceleration. Acceleration is independent of relative motion. The acceleration of a particle measured by an observer in one frame of reference is same as that measured by any other observer moving with constant velocity relative to the first frame. It means that when two frames are moving relative to each other, the acceleration will be same. Consider the two frames S and S prime frames moving relative to each other. The observers in two frames will measure different velocities, but these measures same acceleration moving with constant velocity V naught. As we have seen in above transformations, V prime is equal to V minus V naught, where V naught is the velocity of S prime frame. Differentiating this relation, we will get dV prime over dt, dV over dt, dV naught over dt. As V naught is constant, so dV naught over dt would be 0. Derivative of constant is always 0. So we can write it as A prime is equal to A prime is the acceleration of S prime frame moving with velocity V naught, and A is the velocity of acceleration of S frame. As we see, A prime is equal to dV prime over dt and A is equal to dV over dt. Dear students, the lecture comes to end. Thanks for listening with patience. Allah bless you all. Allah Hafiz.